All right, let's talk about one of the biggest headaches in mobile development: performance. We're going to dive deep into the core reasons why our apps get slow, why they stutter, and sometimes just completely freeze up. And more importantly, we're going to figure out how to build them so they're blazing fast right from the get go.
You know the feeling. We've all been there. You tap a button, and you wait. The screen is totally locked up. A few agonizing seconds later, you get that pop-up of doom, application not responding. It's a terrible experience for your users, and let's be honest, a total nightmare for us developers. But here's the thing. That's not just some random bug. Nope. It's a symptom, a really obvious one of a deeper problem. And today, we're going to get to the root cause.
Okay, so here's our game plan. We're going to tackle this in 5 parts. First, we'll really unpack that unresponsive app nightmare. Then we'll get into the 3 pillars of a high-performance app: how to guard the main thread, how to defeat the memory leak menace, and how to navigate those tricky critical zones. And finally, we'll look at the tools you absolutely need in your toolkit to make all this happen. Right, so that ANR dialogue, it is the absolute worst sign of a performance problem. But it doesn't just appear out of thin air. It's the direct result of a very specific architectural flaw, one that's completely avoidable once you know who the real culprit is.
Okay, so meet the main culprit, or you could say the main character in our whole story, the main UI thread. Just think about this for a second. Every single thing the user interacts with, every tap, every swipe, every single animation you see on screen is handled by this one single thread. If that thread gets tied up doing something else, even for a moment, your entire app just stops. It's that simple and it's that critical.
And honestly, the best way to picture this is to think of a single-lane highway. This is your UI highway. Every car on it is a user tap or a screen update. And as long as the cars keep moving, everything feels smooth and responsive. But what happens when a giant, slow-moving semi-truck tries to get on that same single-lane highway? Instant gridlock. Nothing moves. That's your app freeze. And that leads us right to our first big job. We have to become ruthless traffic cops. The absolute #1 rule of high-performance apps is to keep that single-lane highway clear. It's for fast-moving cars, UI stuff only. All those heavy trucks, they have to take a different road, period. And this right here, this is your cheat sheet for what counts as a heavy truck. I mean, look at this. Making a network call on the main thread, that's an extreme risk of causing a freeze. Hitting a database? High risk. Even just loading and decoding a big image. The rule could not be clearer. The main thread is for UI updates and nothing else. Everything else, and I mean everything, has to get kicked off to a background thread. So how do we actually do that? Well, in Delphi, it's this really elegant 2-step dance with the parallel programming library. Step 1 is easy. You just wrap your heavy lifting, your heavy truck, inside a t-task.run. Boom. That sends it off to a background thread, and your UI is immediately free and responsive. But then comes step 2. And this is crucial. Once that background work is finished, you have to get the results back to the main thread so you can actually update the screen. And how you do that second step, well, it makes all the difference. Okay, so when you send that data back to the UI, you've got 2 main options: synchronize and queue. And this choice, it's a big deal. Synchronize is what we call blocking. It literally makes your background thread stop dead in its tracks and wait until the main thread is ready for it. You can see how that could cause new problems, right? But tthread.queue, that's non-blocking. It just walks up to the main thread's door, drops a message in the mailbox, and then goes on its merry way. The main thread will get to it when it's ready. So the takeaway is simple. tthread.queue is almost always your best bet for keeping things snappy. All right, so we've sorted out the traffic flow, but what happens if the cars themselves are just falling apart on the highway? This brings us to pillar number 2, memory leaks. Think of a memory leak as an engine failure. It might not cause an immediate pileup, but it's going to cause serious slowdowns and eventually bring everything to a grinding halt. And I want you to really let this number sink in. Evidence suggests that for apps that run for a long time, a massive 80% of those application not responding errors are caused, at their root, by memory leaks. 80%. This isn't some small edge case bug. This is very often the main villain of the story. So what's actually happening here? Why do leaks cause freezing? Well, a leak means your app is clinging onto memory it doesn't need anymore. This makes the Android garbage collector's job way, way harder. It has to run these huge, long cleanup cycles to try and reclaim that memory.
Now, for your app to feel smooth, like 60 frames per second smooth, it has to draw a new frame every 16.6 milliseconds. If a garbage collection pause takes longer than that, and trust me, it can, your app misses its deadline. It drops a frame. And what does the user see? A stutter, a hiccup, what we call jank. So how do we fight this? It takes a disciplined approach. You've got to be constantly analyzing your app's memory with a profiler. You need to be smart about big things like bitmaps. You should be choosing data structures that don't waste memory. A great habit is to reuse objects instead of creating and destroying them all the time. And maybe most importantly, use a tool like Leak Canary to automatically find these leaks for you while you're developing. Okay, highway is clear, cars are in good shape. Now for the last piece of the puzzle, the rules of the road. When you've got multiple threads running at the same time and they need to access the same data, you need some traffic lights. Otherwise, they're just going to crash into each other. These traffic lights are critical zones. You can think of a critical section as a one-person-at-a-time room. When one thread enters that room to work with some shared data, it locks the door. No other thread can get in until the first one is done and unlocks it. This is absolutely vital. Without it, you get data corruption, weird bugs, and total chaos. It's how we keep multi-threaded code safe and predictable. But, and this is a huge but, there's a hidden trap here. This quote from Microsoft's own documentation says it all. If you put that lock, that one-person room, inside a loop that runs thousands of times, what have you done? You've basically forced all your parallel workers to stand in a single file line. You've completely killed the benefit of multi-threading. And that really gets to the heart of it. It's all about balance. These locks are essential for safety, but they come at a performance cost. If you use them too much, or you lock way more code than you need to, you've just created a brand new bottleneck. You've taken your beautiful multi-lane highway and turned it back into a single-lane checkpoint, with a huge line of threads just sitting there waiting. So, we've got our 3 pillars. Guard the main thread, plug memory leaks, use locks wisely. Great, but how on earth do you find these problems in a huge, complicated, real-world app? You need the right tools. You've got to have a way to see what's actually going on under the hood. It really boils down to this. You can't fix what you can't see. Seriously, trying to optimize your code without a profiler is just guesswork. It's like driving with a blindfold on. A good, high-precision profiler is the only way to see exactly what your code is doing, where it's spending its time, and to find all those tiny little stutters that add up to a bad user experience. And this is where a modern profiler, something like the Alcinoway Code Profiler, becomes your best friend. It gives you the tools you need to diagnose these exact problems. A threaded timeline shows you if your background work is actually running in parallel. Deadlock detection finds those threads that are stuck waiting on each other forever. Real-time memory analysis helps you hunt down those nasty leaks. It's the complete diagnostic kit you need to build truly high-performance apps. Okay, so let's pull all of this together into a simple health plan for your app. 4 key pillars to live by. Number 1, keep that main thread absolutely pristine, UI only. Number 2, become a relentless, proactive hunter of memory leaks. Number 3, use your locks and synchronization tools like a surgeon, with precision, not like a hammer. And finally, number 4, make profiling a normal, continuous part of how you develop, not just an emergency procedure. And that really leaves us with one final, crucial question you have to ask yourself. Performance isn't just a feature you can sprinkle on at the end. It's not about fixing a few bugs. It is architecture. It's baked into the choices you make from the very first day. So the real question is your app's architecture actually designed for performance? Or, by its very nature, is it destined to freeze?